When we install the Draw client system into your system, we provide you with a 5-step configuration which allows your client to communicate with our server. The first step is to set up the data store path. Now this data store path is the path where your DICOM data is saved, and we want the RT structure also to be saved at the same place. We allow you to start pulling the data at a defined date and time. The next step comes with configuration of the API settings, which allows your client to communicate with our server. The bearer token section over here is auto generated by the server, and the refresh token allows these bearer tokens to be automatically refreshed at 30 days interval. The most unique feature of this system is that you can set up automatic segmentation templates. Now these templates are basically collections of structures which our auto segmentation models will segment for you. You can search for each structure name. So for example, here we are searching for the breast. You can view the various model statistics, delineation guidelines, etc. on our website. Now once you select these structures, they start getting added to the template. So for example, here we have selected 3 structures, then the 4th structure, and you can choose to select the structure that you want for your template. So for example, if you do not want the thyroid in your template, you don't choose it. Once you click create template, it automatically creates a template for you with the following structures chosen. And this can be seen in the admin section, where we can see that the example templates has not been associated with a rule set. Now, in order for the system to run appropriately, we need to configure some rules which tell which automatic segmentation template is to be associated with which type of DICOM file. And the way we do it is that we associated these templates with the DICOM file based upon the metadata tags. So for example, here we are choosing protocol name as the metadata tag, and it will read the value called your choice in the metadata tag if it is available. If so, it will associate this template and it will send this template and the DICOM to the remote server. Now if it does not, it will send it to an unprocessed queue from which there can be manually handled. You can later on review the template that you have decided so that you can understand what structures were there. Now this is a real-time overview of how fast the processing takes place. Although copied DICOM should be refreshed first, but the browser refresh did not happen first. So here we have set up 5 series, of which de-identification took place, and 7 series were actually sent across to the server. The server allows you to view the statistics or processing of the cases also. So if you go to the admin login section, you would be able to see your case list. In this case, we have logged in as the admin, and as you can see that each case is associated with a unique GPU server, and therefore once this GPU server has finished processing, it will automatically delete the file. The client system keeps on polling the remote server to get the latest status. So here you can see some of the statuses change from pipeline activated to copy. And let's go back to the original figure where we had explained how this thing works. So pipeline activation is when the remote server tells the GPU machine to activate the auto segmentation pipeline after it has finished copying the DICOM dataset. And you can see that these status keep on changing. So segmenting means that the GPU server has started the auto segmentation process. In this way, once the segmentations have been completed, these segmentations are retrieved back by the server and then sent to the client. The client then re-identifies the dataset and sends it back to the DICOM storage where it originally came. And you can see that the original time for processing started at 4:17 and all the series have completed processing by 4:49 p.m. This is the power of parallel processing that our system allows. In this demonstration, we will see how the NNUnet models perform as far as the segmentation is concerned. We are giving a visual overview, as you can see the model quantitative metrics on our website. In addition, when you select a model, quantitative metrics like the dice similarity index, the median house draw distance, and the over contouring under contouring distance metrics are also available. Here the mouse pointer is showing the eyes and the optic structures, pituitary, optic nerve, brainstem, and all of these are head neck OAR models which are derived from the head neck model. So you can see that the performance is quite reasonable, and we can see as the contour goes down, we have segmented the DAR structure, which is generally a difficult structure for auto segmentation models to segment. Our larynx segmentation may be different from what you are segmenting, and this is one of the advantages that we have with this system, is that we can accommodate your contouring practices, and in addition we can also train models which are adapting to new guidelines as they emerge. Now in this sagittal section we can show the levels of the spinal cord and the brainstem, and this is as per the guidelines which are followed at our institute. In the next case we will see that the performance of the model in a more thinner patient. Now this patient we have selected particularly because the body mass index is quite low, and this has been a problem when we evaluated segmentation solutions generated from the West, where models were trained on more obese patients. And we can see that because our training dataset was representative of the Indian population, we got a reasonable model performance even for this patient. In fact, all the structures have been drawn. Now let's go on to the breast model. Now this is a patient of breast cancer, and we can see that the brachial plexus are being segmented on the both the sides, the SCF volume, the internal mammary nodal volume. The breast volumes on both the sides are drawn as per the latest ESTRO guidelines. You can see that the contours match the breast contours quite well, and this is because of the training dataset that we have used. Liver, heart, lung, spinal cord, esophagus, everything is drawn. In addition, we have also drawn the left anterior descending artery, and therefore this model promotes the concept of drawing of cardiac substructures. Here we are showing the results obtained from the prostate model, and the prostate model was actually the first model that we trained. And you can see the bowel bag, the nodal CTV, the bladder, and as we come down, the anorectum and the femoral heads as well as the prostate gland are segmented. The penile bulb has also been segmented. Our prostate model performance is quite good for most of the organs, except for the superior aspect of the bowel bag, where there is some variability which is reflected in the modern performance. This is the segmentation of gynae cases. Now this model was quite interesting because we only did this training with a very few number of cases. And you can see that the performance in terms of segmentation of the para-aortic nodal region, kidneys, abdominal organ, etc. are quite reasonable. Here we are highlighting the possibility of nodal substructure solutions, and here external, internal iliac, obturator nodal volumes have been separately drawn. Now as we are showing in this, again this shows how flexible our model is. So we can accommodate different types of guidelines and different types of requirements for your model segmentation needs. The next model that we will show you is new. This is something that we have trained over the last week, and this is MRI substructure segmentation, and we demonstrate using this method that our model is capable of doing multimodality segmentation. These are substructures drawn in the brain like the orbitofrontal region, the eye, retina, cornea, the brainstem, amygdala, hippocampus, and the supratentorial brain, as well as the superior and the inferior part of the cerebellum. As we can see that these complex structures often take more than 30 to 40 minutes for our fellows to draw as per the ESPT and Atlas, and this segmentation can be performed within 3 minutes using our draw system. One of the last segments that we wanted to demonstrate, and this would be quick, is planning structures. Now our physics planning structure drawing is often quite complex in order to meet the OAR constraints for breast, and all of these substructures that you are seeing have been drawn by the draw system. So if your physics planning system utilizes a very formalized way of segmentation of structures, we can help with generating model for generating your substructures.